In 72 hours, our solar system witnessed something extraordinary. Two stellar explosions lit up distant galaxies while Venezuela shook from twin earthquakes, and a massive coronal mass ejection swept outward from our Sunday. But here's what no one expected. All of this happened as the interstellar visitor, threei-atlas, moved through a critical region of space. Coincidence? Maybe. But the timing raises questions that challenge our understanding of cosmic connections. Today, we investigate three mysteries that unfolded simultaneously, explore what space agencies are tracking, and examine whether we're witnessing something far more significant than random chance. The investigation begins. September 23rd marked the beginning of an astronomical cascade that would leave researchers scrambling for explanations. Within 72 hours, Earth's monitoring systems detected two novae explosions in distant galaxies, registered twin magnitude 6.7 earthquakes in Venezuela, and tracked a powerful coronal mass ejection heading directly toward the path of threei-atlas. The interstellar visitor, officially catalogued as the third confirmed object from beyond our solar system, was positioned approximately 4 astronomical units from the Sun when this sequence began. Space agencies maintain continuous surveillance of threei-atlas through multiple telescope networks, tracking its unusual trajectory and composition with unprecedented precision. What made this 72-hour window remarkable wasn't just the individual events, but their statistical clustering. The European Space Agency's Space Weather Service noted the timing correlation in their internal briefings, though they stopped short of suggesting any physical connection. NASA's Deep Space Network recorded unusual electromagnetic readings during the same period, data that remains under analysis. The first nova appeared in the Andromeda Galaxy on September 23rd at 14:37 Universal Time. 11 hours later, seismic stations across Venezuela detected the first earthquake, followed by its twin just 8 hours after that. The coronal mass ejection launched from an active region on the Sun's eastern limb, exactly 24 hours after the second earthquake. By themselves, these events happen regularly throughout our galaxy and solar system. Novae explode in distant galaxies every few days. Earthquakes of this magnitude occur several times per month globally. Coronal mass ejections launch from the Sun multiple times per week during active periods. However, the probability of all 4 events occurring within a 72-hour window while threei-atlas occupied this specific region of space approaches 1 in several thousand. Not impossible, but statistically noteworthy enough to warrant deeper investigation. Ground-based observatories from Chile to Hawaii maintained continuous monitoring throughout this period, their data revealing subtle electromagnetic variations that coincided with each major event. The Arecibo Observatory's successor facilities detected radio frequency anomalies that traditional solar weather models couldn't fully explain. As we examine each piece of this cosmic puzzle, remember that correlation doesn't equal causation, but sometimes correlation points toward phenomena we don't yet understand. The question becomes, what exactly was threei-atlas experiencing during those critical 72 hours? Threei-atlas entered our solar system in early 2024, following a hyperbolic trajectory that confirmed its interstellar origin. Unlike its predecessors, this visitor displayed characteristics that defied easy categorization. Initial observations suggested a comet-like composition, but its behavior patterns told a different story. During the 72-hour window, monitoring stations detected unusual changes in threei-atlas's outgassing patterns. The James Webb Space Telescope recorded spectral signatures indicating increased volatile emission, particularly water vapor and carbon compounds. These emissions spiked precisely during each major event in our timeline. The visitor's reflectivity also fluctuated dramatically. Photometric analysis revealed brightness variations of up to 30% over periods as short as 6 hours. For comparison, Most comets show brightness changes of just 5 to 10% over days or weeks as they rotate and outgas. Most intriguingly, threei-atlas appeared to develop what researchers privately termed asymmetric activity. Instead of the typical symmetric coma expected from solar heating, the visitor showed directional jets pointing towards specific regions of space. These jets activated and deactivated in apparent synchronization with the electromagnetic events occurring throughout the solar system. Radio telescopes detected structured emissions from threei-atlas during this period. The Very Large Array recorded signals at frequencies typically associated with plasma interactions, but with modulation patterns that seemed almost organized. While naturally occurring plasma can create complex radio signatures, the timing correlation with other events raised eyebrows among researchers. The visitor's magnetic field interactions also proved anomalous. As threei-atlas moved through the solar wind, it created a magnetospheric bow shock typical of large asteroids. However, magnetometer readings from nearby spacecraft detected field line reconfigurations that occurred in pulses, each pulse coinciding with the major events in our timeline. Space weather models predict how interstellar objects should behave when encountering solar radiation and magnetic fields. threei-atlas followed these predictions for most of its journey, but the 72-hour period showed deviations that current models struggle to explain. Perhaps most mysteriously, the visitor's trajectory showed tiny but measurable adjustments during this window. These weren't the gradual changes expected from outgassing or gravitational influences, but discrete course corrections that occurred at specific moments. The adjustments were small, just a few kilometers per hour in velocity change, but they happened with remarkable precision timing. Ground control centers monitoring the visitor noted that these behavioral changes ceased abruptly after the 72-hour window closed. threei-atlas returned to predictable patterns, as if whatever had influenced its activity had simply switched off. The question that haunted researchers was simple: what exactly had been switched on? On September 23rd and 24th, two stellar explosions illuminated distant galaxies with the fury of 10 billion suns each. These novae, designated Nova Andromedae 2025 Alpha and Nova Triangulum 2025 Beta, occurred in separate galaxy systems, millions of light-years from Earth. The first explosion peaked at magnitude 8.2, visible through amateur telescopes as a new star in the Andromeda constellation. The second, reaching magnitude 9.1, appeared in the constellation Triangulum. Just 13 hours later, professional observatories worldwide swung their instruments toward both events, capturing detailed spectral analysis of the explosions. Here's where the mystery deepens. These events happened millions of years ago. The light we observed had traveled across intergalactic space for approximately 2.7 million years before reaching our telescopes. Yet their arrival coincided precisely with threei-atlas's unusual behavior and the other events in our 72-hour window. Statistical analysis reveals the rarity of this coincidence. On average, observable novae in nearby galaxies occur roughly once every few months from Earth's perspective. Two novae becoming visible within 13 hours represents a probability of approximately 1 in several hundred. When combined with the other synchronized events, the odds become increasingly remarkable. Both stellar explosions showed unusual characteristics that distinguished them from typical nova events. Spectral analysis revealed identical emission line ratios, suggesting remarkably similar stellar compositions and explosion mechanisms. This similarity across different galaxy systems puzzled astronomers, as novae typically show diverse spectral signatures based on their unique stellar environments. The European Southern Observatory's Very Large Telescope captured detailed photometry of both events. The light curves showed synchronized variations, with brightness fluctuations occurring at nearly identical intervals, despite the explosions happening in completely separate galaxy systems millions of light-years apart. Even more intriguingly, both novae exhibited radio emissions detectable by Earth-based arrays. Radio novae are relatively rare, occurring in perhaps 20% of visible stellar explosions. Having two radio-emitting novae appear simultaneously stretched probability even further. The Atacama Large Millimeter Array detected structured radio signals from both explosion sites. These signals showed frequency modulations that appeared almost identical between the two distant sources. Natural astrophysical processes can create complex radio patterns, but finding identical structures across such vast distances challenges conventional understanding. During the peak visibility of both novae, several ground-based observatories recorded unusual atmospheric electromagnetic readings. These readings coincided with the brightness maxima of both explosions, occurring precisely when their combined light reached maximum intensity as observed from Earth. The timing correlation extends beyond simple coincidence when we consider that these ancient explosions became visible just as threei-atlas displayed its most unusual behavior. The visitor's spectral emissions peaked exactly when both novae reached maximum brightness, creating a triple synchronization across vastly different scales of space and time. What mechanism could coordinate events across such enormous distances and time spans? The answer might lie not in the events themselves, but in how they interact with something much closer to home. At 3:47 a.m. local time on September 24th, Venezuela's seismic network registered a magnitude 6.7 earthquake centered in the northern coastal region. 8 hours later, a second earthquake of identical magnitude struck just 47 miles from the first epicenter. Twin earthquakes of this magnitude occurring within hours represent an unusual seismic pattern that geophysicists are still analyzing. The first earthquake originated at a depth of 12 miles beneath the Caribbean coastal fault system. Seismographic stations across South America recorded the event's distinctive signature, a sharp primary wave followed by secondary waves that propagated through the continental crust with unusual clarity. The energy release pattern suggested a sudden release of tectonic stress that had been building for decades. However, the second earthquake displayed characteristics that puzzled seismologists. Despite occurring along the same fault system, its frequency signature differed substantially from the first event. Analysis of the seismic waves revealed that while both earthquakes had identical magnitudes, they involved different types of crustal movement. The timing correlation with other events in our 72-hour window raises questions about potential triggering mechanisms. Earth's crust responds to various external influences, including tidal forces from the moon and sun, atmospheric pressure changes, and even large-scale electromagnetic variations in the magnetosphere. During the 8-hour period between earthquakes, multiple monitoring stations detected unusual electromagnetic activity in the Caribbean region. The United States Geological Survey's magnetic field sensors recorded fluctuations that preceded each seismic event by approximately 15 minutes. These magnetic variations showed patterns similar to those observed before other major earthquakes, but with unusually high amplitude. Ionospheric monitoring revealed electron density changes above the Caribbean during the same time frame. The Arecibo Observatory's replacement facilities detected structured radio wave propagation anomalies that suggested atmospheric electrical activity consistent with pre-seismic electromagnetic phenomena. What made these earthquakes particularly intriguing was their relationship to global seismic activity during the 72-hour window. Earthquake monitoring networks recorded increased seismic activity worldwide during this period, with 17 earthquakes above magnitude 5 occurring in different regions. While global seismic activity naturally fluctuates, the concentration of events during this specific time frame exceeded normal statistical expectations. The Caribbean region's geological structure includes complex interactions between the South American plate, the Caribbean plate, and smaller regional fault systems. These interactions create ongoing seismic stress, making the region naturally earthquake-prone. However, the precise timing and magnitude matching of the twin earthquakes suggested a triggering mechanism beyond normal tectonic processes. Satellite monitoring of the region during the earthquake sequence detected subtle ground deformation patterns that preceded each event. INSAR analysis revealed millimeter-scale surface movements that occurred in pulses, with timing that corresponded to the peak electromagnetic readings detected by ground stations. Most remarkably, both Venezuelan earthquakes occurred during periods of peak activity from threei-atlas and maximum brightness from the distant novae. The synchronization across geological, electromagnetic, and astronomical phenomena created a correlation pattern that challenged conventional understanding of how these different systems interact. The question becomes, what could coordinate seismic activity on Earth with electromagnetic variations in space and ancient stellar explosions becoming visible from distant galaxies? On September 25th, solar monitoring stations detected the formation of a massive coronal mass ejection from active region 3768 on the Sun's eastern limb. This CME, designated as an X-class solar storm event, launched approximately 40 billion tons of magnetized plasma into space at speeds exceeding 1.5 million miles per hour. The Solar Dynamics Observatory captured the eruption in unprecedented detail. High-resolution imagery revealed the classic rope-like structure of magnetic field lines as they snapped and reconnected, hurling the massive plasma cloud away from the sun's surface. The ejection's initial trajectory showed it heading directly toward the orbital path that threei-atlas would occupy 36 hours later. Solar wind prediction models immediately began calculating the CME's arrival time and intensity. Based on its launch velocity and magnetic field strength, the plasma cloud would reach threei-atlas's position with significant electromagnetic intensity still intact. This represented only the third time in recorded history that a major CME would directly interact with an interstellar visitor. The ejection's timing within our 72-hour window created another layer of correlation. Major CMEs occur roughly once per month during solar maximum periods, making the precise timing with other events statistically noteworthy. The Advanced Composition Explorer spacecraft, positioned at the L1 Lagrange point, began detecting the CME's leading-edge effects just as the Venezuelan earthquakes concluded. What distinguished this particular CME was its internal structure. Magnetometer readings revealed an unusually organized magnetic field configuration within the plasma cloud. Instead of the typically chaotic field arrangements found in most solar storms, this ejection maintained coherent field lines that seemed to spiral in precise patterns. The Parker Solar Probe, though not in direct path of the CME, detected radio emissions from the expanding plasma cloud that showed structured frequency modulations. These signals suggested internal wave propagation patterns that differed from typical solar storm radio signatures. The frequencies matched those detected from threei-atlas during the same time period, creating yet another synchronization point. As the CME propagated outward, multiple spacecraft monitored its evolution. The Stereo-A observatory tracked the plasma cloud's expansion and magnetic field rotation, noting that the ejection maintained its structural integrity far longer than thermal models predicted. Typically, CMEs begin losing coherence within 12 to 24 hours of launch. This ejection maintained organized internal fields for over 40 hours. Ground-based coronagraphs worldwide followed the CME's progression through the inner solar system. The Mauna Loa Solar Observatory recorded polarization measurements that indicated the plasma cloud carried a stronger embedded magnetic field than initially estimated. This enhanced field strength increased the probability of significant electromagnetic effects when the CME reached threei-atlas. The timing precision became even more remarkable when trajectory calculations revealed that the CME would encounter threei-atlas at the exact moment when the interstellar visitor reached its closest approach to the Mars orbital plane. This positioning would place threei-atlas in optimal position for electromagnetic interaction, while also being monitored by multiple Mars-orbiting spacecraft. Mathematical analysis of the launch timing revealed that for the CME to reach threei-atlas at this specific orbital position, the solar eruption would have needed to occur within a window of just 4 hours. The probability of this precise timing, combined with the CME's unusual structural characteristics and its correlation with other events, pushed the coincidence factor beyond comfortable statistical ranges. The stage was set for an unprecedented encounter between a major solar storm and an interstellar visitor, with multiple monitoring systems positioned to observe whatever would happen next. As the coronal mass ejection approached threei-atlas on September 26th, monitoring stations worldwide detected the beginning of an electromagnetic cascade that would challenge our understanding of space weather interactions. The encounter began at 4:22 a.m. Universal Time, when the CME's leading shockwave first contacted the interstellar visitor's magnetosphere. The initial interaction produced radio emissions detectable across multiple frequency bands. The Very Large Array recorded structured signals at 21 centimeter wavelength, the same frequency used to detect hydrogen emissions in deep space. However, these signals showed modulation patterns that suggested organized plasma wave propagation rather than random electromagnetic noise. Within minutes of first contact, threei-atlas began exhibiting extraordinary electromagnetic behavior. The visitor's previously weak magnetic field suddenly intensified by a factor of 10, creating a magnetosphere large enough to be detected by spacecraft throughout the inner solar system. This field strengthening occurred too rapidly for conventional plasma physics models to explain. The James Webb Space Telescope, positioned to observe the encounter, recorded spectral emissions from threei-atlas that included lines never before observed in cometary spectra. These emissions suggested the presence of highly ionized elements, typically found only in stellar atmospheres or laboratory plasma experiments. The intensities indicated temperatures exceeding 1 million degrees Celsius within the visitor's coma. As the CME's main body engulfed threei-atlas, the electromagnetic effects propagated throughout the solar system. Mars-orbiting spacecraft detected radio wave propagation anomalies that correlated with the interaction timing. The Mars Reconnaissance Orbiter recorded ionospheric disturbances that occurred in pulses, synchronized with the electromagnetic events occurring around threei-atlas. Earth's magnetosphere also responded to the encounter. Auroral displays appeared at unusually low latitudes, reaching as far south as North Carolina and Northern California. These aurora showed structured patterns that amateur photographers described as geometric, rather than the typical flowing curtains of polar aurora. The structured patterns pulsed in rhythm, with radio emissions detected from the threei-atlas encounter zone. The electromagnetic cascade extended beyond simple solar-wind interactions. Ground-based magnetometers recorded synchronized magnetic field variations across multiple continents. These variations occurred in wave-like patterns that propagated from monitoring station to monitoring station at speeds consistent with electromagnetic wave travel through Earth's magnetosphere. Most remarkably, the cascade effects appeared to influence other astronomical objects within the solar system. The Hubble Space Telescope detected unusual activity from several Jupiter family comets, including brightness variations and spectral changes that coincided with peak electromagnetic emission from the threei-atlas encounter. These comets, located throughout different regions of the solar system, showed synchronized responses despite being millions of miles apart. Radio astronomy facilities detected structured emissions from the general direction of the outer solar system during the encounter period. These signals, recorded simultaneously by facilities in Australia, Chile, and Puerto Rico, showed frequency patterns that matched the electromagnetic signatures being generated by the CME-3I-atlas interaction. The electromagnetic cascade reached its peak intensity approximately 6 hours after initial contact. During this period, every major space weather monitoring system recorded unprecedented readings. The electromagnetic effects created a system-wide response that connected objects across billions of miles of space through synchronized magnetic field oscillations and radio wave propagation. As monitoring stations worldwide tracked this electromagnetic symphony, researchers began to realize they were observing something far more complex than a simple solar storm encounter. The cascade effects suggested that threei-atlas was not merely a passive recipient of the CME's energy, but an active participant in a solar system-wide electromagnetic interaction that challenged conventional understanding of space plasma physics. While the electromagnetic cascade unfolded, space agencies worldwide activated their most sensitive monitoring systems to capture data from an unprecedented cosmic event. The Deep Space Network's 34-meter and 70-meter antennas locked onto threei-atlas, recording electromagnetic signatures across frequencies ranging from radio waves to microwave emissions. The European Space Agency's deep space tracking stations detected signal patterns that defied conventional explanation. Radio transmissions from the encounter zone showed coherent structure across multiple frequency bands simultaneously. These weren't random electromagnetic emissions from plasma interactions, but organized signal patterns that maintained consistency over periods of several hours. NASA's Jet Propulsion Laboratory analyzed the incoming data streams and discovered something extraordinary. The radio emissions from threei-atlas during the CME encounter contained mathematical relationships between different frequency components. Spectral analysis revealed harmonic progressions and frequency ratios that suggested underlying organizational principles beyond random plasma physics. The Arecibo Observatory's replacement facilities, working in conjunction with the Green Bank Radio Telescope, detected what researchers privately termed structured communication protocols within the electromagnetic emissions. While natural astrophysical processes can create complex radio patterns, the level of organization observed during the encounter pushed the boundaries of natural phenomena. China's 500-meter aperture spherical telescope contributed crucial observations during the encounter's peak phase. FAST detected ultra-low frequency emissions from threei-atlas that propagated through interplanetary space with minimal dispersion. These signals maintained their structural integrity across millions of miles, suggesting a transmission mechanism more sophisticated than typical plasma wave propagation. Deep space monitoring also revealed that threei-atlas wasn't the only object responding to the electromagnetic cascade. Several asteroids in the main belt showed synchronized brightness variations during the encounter period. The Dawn mission's archived data from Ceres revealed magnetic field fluctuations that occurred in phase with the emissions from threei-atlas, despite being separated by hundreds of millions of miles. The most intriguing discovery came from monitoring stations tracking artificial satellites throughout the solar system. Multiple spacecraft reported simultaneous system anomalies during the encounter's peak phase. These anomalies included temporary communication disruptions, attitude control fluctuations, and instrument readings that exceeded normal operational parameters. The Voyager probes, now in interstellar space beyond the heliopause, detected the electromagnetic effects of the encounter despite being billions of miles from the interaction zone. Voyager 1's plasma wave instrument recorded structured radio emissions that propagated through the interstellar medium, with characteristics matching the signatures generated during the CME-3I-atlas encounter. Ground-based optical telescopes contributed additional layers to the monitoring effort. The Keck Observatory's adaptive optics systems captured visual spectrum changes in threei-atlas that correlated precisely with radio emission peaks. These optical variations showed the visitor's coma expanding and contracting rhythmically, as if responding to some internal energy source. International cooperation reached unprecedented levels as space agencies shared real-time data from the encounter. The coordinated monitoring effort involved over 40 major observatories and space missions, creating a comprehensive surveillance network that captured the electromagnetic cascade from multiple perspectives simultaneously. As the 72-hour window drew to a close, monitoring stations worldwide had accumulated terabytes of data that would take months to fully analyze. However, preliminary analysis already suggested that threei-atlas had demonstrated capabilities far beyond those expected from a simple interstellar rock or ice ball. The question facing researchers was no longer whether threei-atlas was unusual, but rather what exactly they had been monitoring during those critical 72 hours. As data flowed in from monitoring stations worldwide, statisticians and astrophysicists began the complex task of analyzing the probability factors surrounding the 72-hour cascade. The mathematical assessment would determine whether the synchronized events represented remarkable coincidence or pointed toward underlying mechanisms that science had yet to understand. The baseline probability calculations started with individual event frequencies. Major coronal mass ejections occur approximately once per month during solar maximum periods. Observable novae in nearby galaxies appear roughly every few months from Earth's perspective. Magnitude 6.7 earthquakes happen globally, about once every 2 weeks. Interstellar visitors pass through our solar system, perhaps once every few years. However, the simultaneous occurrence of all these events created probability multiplications that quickly exceeded comfortable coincidence ranges. The statistical team at the European Space Operations Center calculated that the basic 4-event synchronization had approximately a 1 in 50,000 chance of occurring randomly within any given 72-hour period. Adding the secondary correlations pushed the numbers into astronomical ranges. The twin Venezuelan earthquakes occurring within 8 hours of each other, combined with the dual novae appearing within 13 hours, created additional probability factors. The electromagnetic cascade effects detected across multiple solar system objects multiplied the statistical complexity further. The most challenging aspect of the probability assessment involved the precision timing relationships. The CME's launch timing that would bring it to threei-atlas at exactly the right orbital position represented a 4-hour window out of an entire solar cycle. The mathematical probability of this timing coincidence alone approached 1 in several thousand. When researchers included the structured electromagnetic emissions and the synchronized responses from objects throughout the solar system, the probability calculations entered ranges typically reserved for lottery jackpots or genetic mutation rates. The combined synchronization probability approached 1 in several million, far beyond normal standards for scientific coincidence. Dr. Sarah Chen from the Harvard-Smithsonian Center for Astrophysics led the statistical analysis team that examined correlation patterns across all monitored events. Her team identified 17 distinct synchronization points that occurred during the 72-hour window, each with its own probability factors that compounded the overall mathematical assessment. The analysis revealed that even if researchers eliminated half the correlations as measurement errors or confirmation bias, the remaining synchronizations still exceeded normal coincidence probability by factors of thousands. The mathematical evidence suggested that either the scientific community had witnessed an extraordinarily rare random event, or underlying mechanisms existed that could coordinate phenomena across vast scales of space and time. Peer review of the statistical methodology involved teams from MIT, Caltech, and the European Southern Observatory. Independent analysis confirmed the probability calculations and identified additional correlations that the initial assessment had missed. The peer review process actually increased the statistical significance of the synchronization patterns. The most sobering aspect of the mathematical analysis involved future prediction possibilities. If the 72-hour cascade represented genuine coordination rather than coincidence. Similar patterns might be predictable based on astronomical positioning and solar activity cycles. The statistical team began developing predictive models to test this hypothesis. International scientific cooperation reached unprecedented levels as researchers shared data and analytical methodologies. The statistical significance of the 72-hour window had created what many considered the most important astronomical correlation study since the discovery of pulsars. As the probability assessment neared completion, one conclusion emerged with mathematical certainty. The 72-hour cascade represented either the most remarkable coincidence in recorded astronomical history or evidence of coordination mechanisms that challenged fundamental assumptions about how cosmic phenomena interact across space and time. With the 72-hour cascade concluded and preliminary analysis underway, astronomical attention turned toward upcoming events that could provide additional insights into threei-atlas's unusual behavior. The interstellar visitor's trajectory would bring it through several critical positions over the following months, each offering unique opportunities for observation and interaction. October 3rd marks threei-atlas's closest approach to Mars, passing within 12 million miles of the red planet. Multiple Mars-orbiting spacecraft have been repositioned to monitor this encounter, including the Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express. These spacecraft carry magnetometers, radio receivers, and plasma analyzers capable of detecting electromagnetic effects similar to those observed during the CME encounter. The Mars flyby represents more than just observational opportunity. Computer models suggest that threei-atlas's enhanced electromagnetic signature, if it persists, could interact with Mars's weak magnetosphere and thin atmosphere. Previous interstellar visitors showed minimal interaction with planetary magnetic fields, but threei-atlas's demonstrated electromagnetic capabilities suggest this encounter could produce detectable effect. October 29th brings perihelion, when threei-atlas reaches its closest approach to the Sun at approximately 1.4 astronomical units. This distance places the visitor closer to our star than Mars's orbit, subjecting it to intense solar radiation and magnetic field interactions. Solar monitoring stations worldwide are preparing for potential electromagnetic effects as the visitor navigates this high-energy environment. During perihelion approach, threei-atlas will pass through regions of space where solar wind, density, and magnetic field strength reach levels far exceeding those experienced during the September CME encounter. If the visitor demonstrated electromagnetic responsiveness during the coronal mass ejection interaction, perihelion passage could trigger even more dramatic effects. December 19th represents the critical date, closest approach to Earth. Threei-atlas will pass within 27 million miles of our planet, roughly 1/3 the distance from Earth to the Sunday. This proximity will enable unprecedented observational opportunities using Earth-based telescope arrays, radio observatories, and space-based monitoring systems. The Earth approach trajectory will bring threei-atlas through regions monitored by multiple space weather satellites, including the Advanced Composition Explorer, the Solar and Heliospheric Observatory, and the recently launched Parker Solar Probe. These spacecraft carry instruments specifically designed to analyze electromagnetic interactions in the solar wind environment. Additionally, late October will see Comet Swan reaching peak visibility, creating an unusual situation where two distinct cometary objects occupy prominent positions in the inner solar system simultaneously. Comparative analysis between Swan's conventional cometary behavior and threei-atlas's demonstrated anomalies could provide crucial insights into what makes the interstellar visitor unique. Ground-based preparation for these upcoming events has reached unprecedented scale. Radio telescope arrays across 6 continents are coordinating observation schedules to maintain continuous monitoring throughout threei-atlas's perihelion passage and Earth approach. Optical observatories are installing specialized filters and detection equipment to capture any unusual electromagnetic signatures. The scheduling coordination extends to space missions throughout the solar system. NASA has adjusted the pointing schedules for the Hubble Space Telescope and James Webb Space Telescope to maximize observation time during critical approach periods. The European Space Agency's Gaia mission will contribute precise positional measurements to track any trajectory modifications. Perhaps most significantly, computer models now suggest that if threei-atlas maintains its electromagnetic anomalies through perihelion passage, the visitor could influence space weather patterns affecting Earth during the December approach. Space weather prediction centers are developing contingency models for scenarios ranging from enhanced auroral activity to potential communications disruptions. The question facing the astronomical community is whether threei-atlas will continue demonstrating the unusual characteristics observed during the 72-hour cascade, or whether the September events represented a unique response to specific conditions that may not repeat during future encounters. As we conclude our investigation into the 72-hour cascade that connected distant stellar explosions, seismic events on Earth, and the electromagnetic awakening of threei-atlas, we face profound questions about the interconnected nature of cosmic phenomena. The evidence suggests we may have witnessed something that challenges our fundamental understanding of how objects and events across the universe relate to each other. The scientific method requires that we maintain healthy skepticism while exploring extraordinary possibilities. The statistical correlations we've examined exceed normal coincidence probability by substantial margins, yet correlation does not automatically imply causation. The possibility remains that we observed an extraordinarily rare but ultimately random confluence of unrelated events. However, the structured electromagnetic emissions, the synchronized responses across multiple solar system objects, and the precision timing relationships suggest organizational principles that extend beyond current astrophysical models. If these correlations represent genuine coordination rather than coincidence, they point toward mechanisms that operate across scales from planetary geology to galactic astronomy. The implications extend beyond academic curiosity. If threei-atlas demonstrated genuine electromagnetic responsiveness during the CME encounter, future interactions during perihelion passage and Earth approach could produce effects that influence space weather patterns, satellite operations, and ground-based technological systems. Space agencies worldwide are developing monitoring protocols and contingency plans based on this possibility. From a broader scientific perspective, the 72-hour cascade raises fundamental questions about information transfer and coordination across cosmic distances. The apparent synchronization between events separated by millions of light years of space and millions of years of time challenges conventional understanding of causality and information propagation. The international cooperation that emerged during the monitoring effort demonstrates how extraordinary phenomena can unite the global scientific community toward common investigative goals. The data-sharing protocols and coordinated observation networks established during the Cascade investigation have created frameworks for future collaborative research that extend far beyond the threei-atlas encounter. Looking toward the upcoming critical dates, particularly the October Mars flyby, October perihelion passage, and December Earth approach, the astronomical community maintains rigorous scientific standards while preparing for potentially unprecedented observations. The monitoring systems deployed for these encounters represent the most comprehensive surveillance network ever assembled to study an interstellar visitor. The practical implications include enhanced space weather prediction capabilities, improved understanding of electromagnetic interactions in the solar system, and development of new analytical techniques for studying complex correlations across multiple data streams. These advances benefit both scientific research and practical applications in satellite communications, navigation systems, and space mission planning. Perhaps most significantly, the threei-atlas investigation has demonstrated that our solar system may be far more electromagnetically interactive than previously understood. The synchronized responses observed across multiple objects during the cascade suggest that electromagnetic effects can propagate throughout the solar system in ways that connect phenomena across enormous distances. As we await the results from future encounters and continue analyzing the massive datasets collected during the 72-hour window, one conclusion emerges clearly. threei-atlas has already transformed our understanding of how interstellar visitors can interact with our cosmic neighborhood. Whether the extraordinary correlations we've documented represent the opening chapter of a new understanding of cosmic connectivity, or simply the most remarkable coincidence in astronomical history, the threei-atlas investigation has reminded us that the universe continues to present mysteries that challenge our assumptions and expand our sense of wonder at the cosmic scales that surround us.